Welcome everyone. For this video, we are going to discuss the relationship of electric current, resistance, and voltage. Electric current is a flow of a charge, which means that all charged particles, whether in solid or in liquid, will flow on a certain object. In metals, current is the movement of negative charge, which is the electrons, while in gases and electrolytes, such as the sodium chloride solution, both positive and negative charges may be involved. Current, in other definition, is the rate at which charge is flowing in a circuit, which means that it is the number of charges that passes through any given point of a circuit per unit time. Based from this definition, we can have the formula: the current is equal to the charge divided by the time. So in an equation form, it will be symbolized by I is equal to Q over T, where your I is the electric current, and Q is the electric charge, and T is the time. Current is measured in ampere, symbolized with capital letter A. As one of the fundamental units of physical quantities, 1 ampere is equivalent to 1 coulomb per second. Imagine that this is a flowing particles, charged particles. So let's take note that this part here is not a wire. So we can have this that as a charged particle, positive charges may flow as well. So at this any given point or this any given area, this imaginary plane, all this amount of charges flowing on this specific area is now called as our electric current. There are two types of current flow or electric current flow. We have the conventional flow of current, where it is moving from the positive to the negative, while there is the other one, which is called as the electron flow, which is from the negative moving to the positive. Scientists first thought that positive charges flow from the positive terminal of a cell to the negative terminal of it. I am talking about a dry cell, or most common in Filipinos as battery. This is called the conventional current direction. That's from positive to the negative. However, it was found that a current in a metal wire is in fact a flow of negatively charged electrons in the opposite direction. Nevertheless, the conventional current is still being used as of today. Let's have example. A hair dryer draws a current of 3 amperes. If it is switched on for 5 minutes, how much charge and how many electrons have passed through it? For our solution, so we have by electric current, which is equal to the charge divided by the time. Our electric current is equal to 3, and we are looking for the amount of charge, and the time it takes for this electric current to be used is 5 minutes. So converting 5 minutes into seconds, then we can calculate for Q. So we have 3 . So we have Q now is equal to 900 coulombs. So in this case, we multiply the time taken to the electric current. So we have here 300 multiplied to the electric current, which is 3 amperes. So we came up with 900 coulombs as the amount of charge passed through the circuit. Now, for the number of electrons, one charge of electron is equivalent to 1.6 times 10 raised to negative 19 coulomb. So to identify the number of electrons present, it will be now equal to 900 coulombs divided by the charge of an electron, which will give us an answer of 5.625 times 10 raised to 21. So this is the amount of electrons passed by the circuit during this time that has been switched on. Moving on, the electromotive force, on the other hand, or EMF, of a battery is the energy transferred or work done to a unit charge from chemical energy of the battery when the charge passes through the battery. The electromotive force is the one that will push the electric charges to flow in a circuit. So this will happen when the chemical energy from the battery uh, transform into electrical energy. The EMF of a battery is 1.5 volts if a 1.5 joules of electrical energy is transferred to each coulomb of charge. The unit of EMF, or the electromotive force, is in volts, symbolized with capital letter V, which is equivalent to 1 joule per coulomb. Based from this, we can calculate for the electromotive force, or EMF, with this equation. That the voltage, or rather the electromotive force, or EMF, is equal to the work done divided by the charge. What's the difference between EMF and the potential difference, or PD? Let's take a look. The potential difference, or PD, or the voltage across 2 points in a circuit, is the amount of electrical energy which changes into other forms of energy when unit positive charge passes between these points. So looking into this diagram, so if I have an EMF of 4 volts, so we have 4 joules of energy given to each coulomb of charge, meaning that the EMF is present within the battery or the dry cell. So this will be the one who will push the electric current on the circuit to move on a certain load. The load is either a bulb or any appliance that will consume the energy that has been given by the battery. So in this case, 1 joule of energy change into heat, and the heat and light energy by each coulomb of charge. So here, 1 volt of coming from the EMF, or coming from the dry cell or the power source, has been consumed. Then the remaining 3 volts will be consumed by the other load. So we have here 3 joules of energy change into heat, and heat and light energy by each coulomb of charge. So if you're going to look into this diagram here, a schematic diagram of a series circuit has consumed all 4 volts that came from the dry cell or the battery. So from the current that has been passed, so the energy is being carried by the current going to the load. So 1 joule has been charged or has been changed and it consumed 1 volt. And then we have here 3 volts has been consumed again by the other load. Now, when we say potential difference, it is between from one point to another point. So we are going to measure this kind of quantity from, for example, at this point here and in this point over here, and not the totality of it, because the total amount of uh, potential energy that is being placed on this is equivalent to 4 volts, which is just 4 joules of energy. It's being placed to the charged particles. Let's look in example number 2. Let us consider the circuit below. We have a 6-volt battery as our power source. Then I have here points A, B, and C. And I have 2 loads with 2 different values of resistances. Let us take note that voltage, current, and resistance follows the Ohm's law. If you're going to go back to your junior high school science, Ohm's law is the relationship of these 3 quantities where the voltage is directly proportional to the current and to the resistance. With this, we can say that the potential difference from point A and B is equal to the current and to the voltage, to the current and to the resistance that's placed between these 2 points. In this case, the potential difference across A and B, so here we have 1 ampere of current that is flowing on the circuit, and then we have 4 ohms of resistance from this load that give us a 4 volts of potential difference between A and B. Now, between B and C, we have 1 ampere of current that is flowing on the circuit, and then 2 ohms of the resistance from this load. So the volt or the potential difference between points B and C is equal to 2 volts. So we have the total number of voltage or the EMF coming from this battery, which is equal to 6 volts. Now, if the voltage or the potential drop at C is equal to 0, what will be the potential drop at point B and at point A? If the potential drop at point A is 0, what will be the potential drop at point B and point C? In this case, if C is 0, therefore the voltage drop at B will be equal to 2, while the voltage drop at A will be equal to 6. If 0 is the voltage drop at point A, therefore the voltage drop at point B will be negative 4. On the other hand, if the voltage drop at point A is 0, the voltage drop at point C is negative 6. Since we are talking about resistances on these loads, what is a resistance? A resistance is a measure of the opposition to current flow in an electrical circuit. Looking into this diagram, the voltage or the EMF is the one that will push the current to flow on a certain material, or in this case, the electrical wire. And then the current will be the one who is flowing on this circuit. Now the resistance is the one that will oppose or hinders the free flowing of the electric current on a certain material. The unit of resistance is ohms. Resistance is measured in ohms and it is symbolized by a Greek letter omega, where it is named after George Simon Ohm, a German physicist who studied the relationship between the voltage, the current, and the resistance, which he is credited for formulating the Ohm's law. The resistance of a conductor is due to the collisions between the electrons and the vibrating ions called as the crystal lattice, and the electrons and the defects in crystal lattice at very low temperature. Let's try to look into a simulation on how we are able to connect the relationship between voltage, current, and resistance. So we have here the simulation for Ohm's law by Pet, Colorado. So we have here that the equation, the voltage is equal to the current times the resistance. In this equation, we can say that the relationship between voltage to the current and resistance is directly proportional. That if we increase the current, the voltage will increase as well. Or if we increase the resistance, the voltage will increase as well. Now, if I have a 3 volts battery inserted in this circuit, let us try to look into the amount of current that will be flowing on this circuit if we are going to raise the amount of resistance present in the circuit. So lower it down, make the electric current much bigger. So there is a great amount of electric current that is flowing on the circuit. Now, making the resistance higher, so you will notice this small dots here. This represents resistivity, which I will discuss a little later. So here, the amount of current is much smaller. It's 3 milliamperes compared to when the resistance is much smaller. We have a less amount of resistance and the current is at 300 milliamperes. So setting our resistance at 200 ohms, we'll try to increase the voltage at this point. We'll try to have a voltage of 4.5 volts. So you will notice that there is an increase in the amount of current that is flowing on the circuit. So this is how the relationship, so I have now 6 ohms and the amount of current also increases. So the greater the voltage, the greater the amount of current that will flow. So that's the relationship or by the voltage, the current, and the resistance presented in Ohm's law. So the resistance R of a conductor is defined as the ratio of the potential difference V across it to the current I flowing through it. So given that definition, you can come up with an equation as this. The resistance is equal now to PD, or the potential difference across the conductor, divided by the current through the resistance. Current through the conductor. So in symbols, we can come up with R is equal to V over I. Let's try to look into the relationships through graphs of current and potential difference. So we have here a graph of I and V, the current and the potential difference. Their I-V graphs are straight lines through the origin. They obey Ohm's law, which states that the potential difference across a conductor is directly proportional to the current flowing through it, provided that the temperature is constant. Hence, we call it as the ohmic conductor. So all of these conductors that follows the Ohm's law is known to be as the ohmic conductor. Now, for a non-ohmic conductor, so the IV graph bends over V or over as V and I increases, indicating that a given change of V causes a small change in I at larger values of V. That is, the resistance of the tungsten wire filament increases as the current raises its temperature and makes it white hot. In general, the resistance of metals and alloys increases with temperature. So the moment that the temperature rises, then you will notice that there is now a glow on the filament of or a filament lamp. And you will notice that this is a concrete example of a non-ohmic conductor. Let's look into the effect of temperature on the resistance of a metal conductor. So let's try to look into the difference between a cold wire and a hot wire. For metals and a lot of insulators, when temperature is raised, the lattice ions vibrate more vigorously, increasing the frequency of collision between electrons and the lattice. The average drip velocity is reduced and the resistance therefore increases. So the more that it is hotter, the more movement of the lattice ion inside of a warm wire. The resistance of a conductor depends on its length and thickness. So looking into the relationship, we have the R, or the resistance, is inversely proportional to the area, while it is directly proportional to the length. So the lower or the smaller the surface area of a given wire, this case, you notice that there is a little amount of resistances present, and there is a great number of less number of electrons that is flowing, while a greater area, so you will notice that there is a great amount of charges flowing on the material. So the longer naman the length of a certain material, the greater the resistance that we have, because the greater the travel time and the greater that it travels by the charges. Notice that the electrons seem to be moving at the same speed in each one, but there are many more electrons in the larger wire. This results in a larger current, which leads us to say that the resistance is less in a wire with a larger cross-sectional area. The length of a conductor is similar to the length of a hallway. A shorter hallway would allow people to move through at a higher rate than a longer one. So a shorter conductor would allow electrons to move through at a higher rate than a longer one too. In this case, this relationship is now called as the resistivity, as R is inversely proportional to the area, and R is directly proportional to the length, then we get that the R will be equivalent to L over A. Hence, R is equal to rho L over A, where rho is called as the resistivity of the material, and the unit of resistivity is in ohm meter. Different materials have different resistivity. So for an example, we have the good conductors. Copper and silver has a resistivity of 1.7 and 1.6 times 10 raised to negative 8 ohm meter, while a conductor, nichrome and graphite have 1.1 and 8 times 10 raised to negative 6 ohm meter of resistivity. Looking into an insulator, you have a greater amount of resistivity, such as this quartz, with 5.0 times 10 raised to 16 ohm meter. Let's try to look into a simulation to learn more about the relationships of resistivity to the resistance. So we have here that R, the resistance, is equal to the resistivity times the length divided by the area. So let's take note that the lesser the area, then we have a larger resistance. The greater the area, then the lesser the resistance. So here, we're going to look into, let's make our length much bigger. So you will notice that as the length increases, R also increases. But if we are going to make our area, so you notice that as the area increases, R decreases as well. So if we have a greater area, we will have a lesser resistance. So if we are going to make it longer, still we have a lesser resistance. Even if we have longer length but bigger area, then we have a smaller resistance. And you will notice that the resistivity is very low, which means that this material is a good conductor of electricity. Making it bigger, so you will notice the dots represents the air resistivity. So as the resistivity increases, the resistance also increases, making it a good instrument. Okay, so making the area smaller makes our resistance bigger, making this material now a good insulator. Okay, so again, this is from PET, the Colorado simulations. So from here, the different resistivities, let's have example number 3. Let's find the resistance of a copper wire if its length and radius are 5 meters and 2 millimeters respectively. So for our solution, our equation is that R is equal to rho L over A. And for the copper wire's resistivity, it is equal to 1.7 times 10 raised to negative 8 ohm meter. And the length of 5 and an area which will be calculated as pi r squared. And we have a radius of 2 millimeters, which is equal to 0.002 meter. Then our area is equivalent now to 1.2566 times 10 raised to negative 5 square meter. Then R, the resistance, is equivalent to 1.7 times 10 raised to negative 8 times 5 divided by 1.2566 times 10 raised to negative 5. So we have here the 1.7 coming from the resistivity. 5 here is our length, and 1.22566 times 10 raised to 5 square meter is our area. So our final answer, so the resistance is equivalent to 6.76 times 10 raised to negative 3 ohms. So I hope that you have learned something from this lesson that we had. Okay. So for our do-it-yourself activity, so I want you to answer the following questions on your own. And let's try to look into if you're able to come up with the correct answer. So thank you very much, everyone. I hope you have learned something about the relationship of electric current, resistance, and voltage.